Okay, so welcome everyone to this lunch seminar, which is going to be about how to model double skin facades and windbreaks. Thank you for joining me. And this is just it's just one of the topics that I was doing a little bit on my free time. It's my pet project. And I just wanted to share it with everyone else. I think there are, a couple interesting things, I guess, for everyone. Even though here in the group we work a bit on other topics, but still. So most of you know me, but those who don't know, my actual background is in civil engineering, and I was specialized in structural engineering, wind engineering. I was in a lot of computational fluid dynamics, and this is actually the picture of one of the projects I was working on back in my civil engineering days and wind engineering days. It was the ELT. It's going to be one of the biggest telescopes, optical telescopes, that is currently built in Chile. There's actually, like, if anyone interested, you can find the webcam, so I think you can see the construction right now happening in real time. It's quite amazing. A huge structure, 90 meters in diameter, and the work there I was doing is actually I was doing like computational fluid dynamic simulations, and we had to verify the effectiveness of wind screens. So this is kind of like what brought me to this topic, and I just wanted to keep on doing it, working on it on free time, and eventually we published a paper. So I will try not to take too much of our time. I'm going to go for 1 hour so we can all have lunch. I'm going to talk a little bit about what the double skin facades are. I'm going to tell you how they're being modeled, or how we deal with them right now in engineering, and what is wrong with the way it's being dealt right now. And then I will show you one of the methods I worked on to actually model these structures, and I will show a couple practical applications. So the double skin facades can be permeable. These are the structures that people put on outside of very tall buildings, and it has a lot of advantages. Architects love it. One, it's architecturally interesting, it's beautiful. Some people find it beautiful, and I guess that it's a subjective thing. But another one is the stability of very tall buildings to wind loads. So some of you may know the phenomenon of vortex shedding. Is when vortices detach from the building, which can cause oscillations of the building. So these kind of double skin facades prevent it from happening, or they make the effects much lesser. Another one is another reason why people do this is for energetic reasons. So they can provide shade for direct sun. So, for example, when these louvers on this tower in Doctoral, they can change their angle so that you can protect more from sun, more or less. Now, obviously, these are very big structures, and they have to be designed to wind loads. And currently, the best way we can design to wind loads, you can consider the golden standard, is to do wind tunnel testing of different structures. So you put a scale structure in the wind tunnel, and you let the wind blow on it, and you measure the pressures, and there is some procedure how to do it properly. And the difficulty there is, to do it properly, you have to scale, because obviously the small model is not the same, and there are scaling laws. And the problem is the double skin facades, it's quite difficult to scale them. And another one is to measure pressure. When these structures are scaled, they become so small, you cannot to properly scale them. For example, the openings are still big, so the pressure is not uniform, not the same. So the pressure sensors on the facade behind this double skin might not measure what would be actually happening in the full scale structure. So Yeah, this is an example, actually, a picture from the Polytechnico di Milano tunnel, which is one of the biggest tunnels there. So obviously the other way is, well, let's try to do the computational fluid dynamics way. Let's try to run some simulation and see what happens. And the advantage is you get a complete flow field everywhere. The problem is, I don't think anyone here did CFD practically, but the main problem is, to give you an idea, to model a 10 centimeter by 10 centimeter grill, you need around 50 million cells. And when we were doing these simulations, we saw like, we can do 10 centimeter by 10 centimeter to model the full structure. It becomes impossible. Not in the best supercomputers right now will be able to do it. So yeah, it's impossible to resolve all geometric details to get the flow through this. For example, if it's a perforated screen, the holes would be, the diameter would be like 2 millimeters, 3 millimeters. And for example, the telescope I showed before is like 90 meters diameter. So what is done usually is, sorry. Is we take our Navier-Stokes equation, which is a classical equation that is used in fluid dynamics. I usually don't like putting equations on the screen, but I get it. This is an important one. So, and it's not actually that much, not that difficult. This is basically force equals ma. Here you have the derivative of a speed, so you basically have something like an acceleration. I'm going to be a bit hand-wavy about it, but don't. So this is basically our acceleration, the density basically like a mass, so ma, and these are all the forces. So we have pressure forces. This huge term is just viscous forces. This is bulk viscosity, so it's another viscous force. So basically the forces that happen inside a fluid. And then the last term is just some other terms, force terms that are in the fluid that is being modeled. So it can be like buoyancy, gravity, stuff like that. So what usually is done in order to model at least somehow these force things is to add a term which is a sinc term, and so instead of this rho Ri, we have this term, which was introduced by Professor Philip Horkheimer. I added him because he is actually alumni of ATH, so I thought it's quite interesting. And basically what this does, it just adds more resistance. So the perforated thing would be providing resistance, and there are two terms here. One is proportional to speed and viscosity of a fluid, and the other one is just proportional to the square of a fluid, a square velocity of a fluid. And so usually this first one is called the viscous term, and the second one is a momentum or inertial term. And the problem which arises here is like, okay, we can model these screens by adding this Darcy-Horkheimer term, but how do we choose these matrices, the D matrix, because they have these coefficients that introduce the resistance. What is done right now is one option is to go by empirical relations. So we take a perforated screen, we see how many holes are there, and how many, what is the full area, what is the empty area, and we can calculate using these empirical coefficients. We can calculate what will be the resistance terms. One thing to note that only in one direction, only fx, but before if you saw it was actually like it's a tensor. Another way is to do a lot of experiments and to do the pressure curve fitting. So you measure your loss of pressure before and after the screen, the perforated screen, and there is a law, which we can, there's the Permeable law, and we measure a couple points, and then we fit to this law, and so we get dx and fx from fitting. What are the problems with both of these methods is that they look only in a single flow component. So they consider, okay, the flow is coming into the screen, orthogonally to the screen, there is some pressure before the screen and after, and then we get the one resistance coefficient, but we don't know how to set other resistance coefficients here. So that's the first problem, that it only does one flow component, and the second one is that it accounts only for pressure drop. But what's happening often with these perforated screens is that they also introduce flow deflections, which is quite obvious in case of louvers, where they're not just perforated screens. So if the flow would be coming in orthogonally, it's going to be deflected. I mean, I think most of you will find it quite intuitive. But also, even if it's not a louver, but just a perforated screen, the flow that would be coming into the screen at a certain angle, gonna come out at a different angle, because there is some resistance being introduced in a tangential direction. So, for example, here, if the flow will be coming in at 45 degrees, the outflow gonna be deflected, let's say at 40, for example. I mean, it is gonna depend obviously on the screen and the configuration. And unfortunately, no one was thinking about it, looking at it. So, like, if you would go online, it would just look, well, how do I set up the coefficients for a perforated screen? Here's I took this from this manual on this SimScale documentation, which is like a computational fluid dynamics code. And they propose like an algorithm how to set. They obviously set only one direction. And then what they do is they say, well, for the other two directions, let's just put infinite, like very big number. And my question is, like, if you look at this picture, can you guess what's wrong with it just by looking at it? So the arrows indicate the flow. And do you find anything strange with it?
I would expect turbulences after the screen.
Yeah, I mean,
the flow looks pretty laminar still after.
Yeah, it's okay. I'm not diving into turbulence. This is the state.
This is supposed to be the boundary of your screen.
So this is the screen. It's inclined and it's in a duct. So the flow is coming in. There's some pressure obviously before and then some pressure after, but that's not. I don't want to look at it. I want just to look at the flow.
But in truth, this screen, what are the boundaries of your simulation? I mean, isn't there a medium also below and above?
No, we can think of it as a frictionless duct.
Okay. Because it's a bit odd that you have this downward.
Yeah. So the thing is, we can see that the screen aligns the outflow exactly perpendicular to the screen. And if you would put an actual screen in a duct, it's not going to change the flow that much. Like, it's not going to all of a sudden, if it's some big piece of metal with like long tubes that are going to redirect the flow, yes. But if it's just a screen, it's not going to redirect. So obviously the assumption that they use when they were setting up of setting other resistance coefficients to very high values makes no sense. Like, makes no physical sense. So what I try to do is to look into how do we set the other coefficients. So in this, I think, so in these terms, people know how to set one direction, the one that is perpendicular to the screen. How do we set the other ones? And there, obviously, one option we already showed you. People say, okay, let's put some big number. Another option, people say, let's put 0, which is not as bad. It's not going to deflect the flow perpendicular to the screen, but it's also not going to introduce any flow deflection, the thing that I mentioned earlier. So if we put another coefficient 0, there's going to be no flow deflection at all. So the way to look at it is to take the original equation, and the way I approached it is what I call an engineering approach. An engineering approach is kind of like, let's throw away everything we cannot deal with and see if our assumption still holds. So obviously, solving the Navier-Stokes equation is the millennium prize, $1 million. I mean, we cannot do that, at least not yet. So what we do is, what I did is I looked at it and I'm okay, what things can we disregard? So the first thing I did is I considered a steady state case, so no variability in time, to get rid of this term. Another one is, in case of screens on big structures, the viscosity is not that important. The inertial coefficients are much more important. Viscosity, at least in air, on a big scale, not that important, so we can almost disregard it. So we can disregard this huge term and the diagonal, the Darcy matrix, this one. And also this one, because this one is viscosity. So we are basically left with just the inertial coefficients, the pressure, and this is the part of substantial derivative, material derivative. And another thing that we can do is we can also assume the screen infinite in all directions. So let's not consider effects of the edges, anything like that. And with all of that simplifications, we can simplify the very complicated equation from before to something like this. And I wrote it down not in indices so that it's more obvious. And this provides much more intuition on what is happening. And why is that? Is because if we also look, if you also look at the screen from macroscopic level, we will see we can write the forces on a portion of the screen in the volume. So we can look at the pressure before and after, and also at the flow components before and after. So we have two sets of equations. One looks on the macro level, and the other one describes the flow through the porous medium. And what it allows us is to see exactly that the changes, for example, like this equation, for example, the changes in y direction are going to be the ones affecting the forces on the screen in y direction. The change in pressure is going to affect the forces in x direction, and the change in z direction of flow is going to affect the forces in z direction. And another good thing is, even though the solution of this equation is quite ugly, I don't know the other, but there is an analytical solution to it. So after that, it becomes quite straightforward. What we can do is we can put a screen in a duct, measure these forces, and then using the analytical equations, fit the flow so that these coefficients would fit to all the forces. So unlike before, where we had only one coefficient effects, here we get all the coefficients. So does this work? So we try to put a wired mesh in a duct, and we did some. We run our optimization. So the circles are what forces are measured on the actual screen. The line is an analytical solution of what we would expect if we would solve these differential equations with the coefficients that we found in the square optimization. And then the marks, the crosses, are what are the forces from the computational fluid dynamics software that uses porous volumes or porous areas with the coefficients that we found. So the good thing is that computational fluid dynamics software solves the solution there, even though it's a finite volume solution, it's very close to the analytical solution that we found from the equation that I showed before. And that the behavior itself was captured. So we captured not only the forces in X direction, but also the forces in Y. So we tried it on other types of screen. So we tried on a perforated screen. This one is not a physical, kind of a bit of fake example, because the thickness of the screen is 0. And so this one was purely numerical one. And obviously when we have this non-physical infinitely thin screen, there is no deflection in Y direction, no forces in Y direction, we have only forces in X. If the screen has like a bit more thick, it's going to introduce some tangential forces when the flow is inclined. And if the screen is the thickest, obviously, like this one was 4mm screen, I think. So we were, the forces start to become quite substantial as compared to the X. I'm sorry, I guess in the public, maybe it's not very clear, this graph. On x-axis, we have the angle at which the flow is incoming. So the y-axis are the forces, but the x-axis is the angle at which it's incoming. So when the flow is incoming orthogonally, obviously there is no tangential forces. It just goes exactly through the screen. But for example, at a 45-degree angle, the tangential forces become quite important. This is the case for louvers, the same thing. Interesting that both analytically and in practical case, there was a reversal of sign of force. So when if the angle is very high, at the angle of attack is very high on these louvers, the force actually changes direction. The Y component we could not fit as perfectly as we want to, and that might be because we disregarded the viscous term, or maybe the forces we had themselves were not very precise. It would be nice to have like some uncertainty quantification on these results, or some actual internal testing.
Question?
Yeah.
The angle is with respect of the dark part, with respect to the z-axis, right?
The angle is if you think of a screen, how so that would be the rotation around z-axis of a vector.
Why is it then not symmetric with respect to 0 attack angle?
Because these are louvers, so and they're put at 45 degrees. So that's a very nice observation. That is something we expect. So for something that is symmetrical, the forces are going to be symmetrical, right? We get an even function, obviously. But because these louvers, so if you think of like an inclined louver, right? And then the force, when it comes orthogonally, it's gonna give you some resistance, but this change, plus and minus, is not the same with respect to geometry. So geometry itself is not symmetrical. Okay. Obviously, like the minimum resistance you would expect somewhere around the same inclination as a louver, which was 45 degrees. And yeah, here it gets close to 0, but not exactly. These are expanded meshes. It's like let's not go too much into those. And then expanded meshes when we vary direction, not like if we distinct, also with the louver, not in one plane, but in the other plane in that direction. So already half an hour, so wrapping it up. What can be improved is one is it would be nice to do, as I said before, to have some internal tests on or result models with uncertainty quantification, so that we have more certainty on these numbers that on the courses that we had. These ones were from computational fluid dynamics simulations, but yeah, there's, as I said, it was a project that was on the free time, so we did not do to go too much in detail in there. Another thing is it would be nice to consider viscous effects. As I said before, we had to disregard it to have an analytical solution of the equation. Or turbulence effects, the same. Those are not considered. The topic becomes quite complicated, exponentially complicated, because there is a need for closure models and things like that. The edge effects are not considered. As I said, I assumed an infinite screen in all directions when I was deriving analytical equations. So what happens close to the edges is not going to be what the model is going to simulate. Open form code, I found that there are some bugs in it related to numerical things. I don't think it's interesting to most of the people here, but and another possibility is to have something called sync buffers. Again, it's something to do with modeling. So instead of modeling a volume or like a part of a domain that has resistance, it's possible to introduce just like a surface and then introduce custom resistant coefficients there. Final thoughts. Now that we do a lot of machine learning and a lot of data-driven things, I think it's still good to sometimes just look at the differential equations that describe the physics. And often engineering code just gets the job done with simplifications are still reasonable. So that is it. And if you have any questions, I will be happy to answer.
I think there are some also online, so you can unmute in case you want to ask. I guess from my point of view, I wanted to ask you, the standard way of treating this in structural engineering is to simplify the forces as point loads and apply some coefficients, I suppose, and then try to design for it. Do you think this analysis can be translated into something like this? Because it's not going to be that the actual engineering, structural engineering officers are going to want to see if this simulation works. Would it be translated into a load they can handle with their software is the question. This is all they can do.
I mean, obviously the question is first obtain the loads, so after simulation, but then yeah, it's possible to transform it into like a
dynamic,
a pressure
map.
Yeah, so usually what happens is also like when they do wind tunnel tests. I don't think I have a picture here that would be nice to show, but like a building would have tiles, would be tiled into like these areas, and each area would have a pressure tap, and that pressure tap somehow gets the reading from that pressure tap gets extrapolated to all that area. So what yeah, unfortunately, I don't have anything that I could show right away, but yeah, usually it's just like a pressure map.
Yes, which would be dynamic, so it would have to be run with the dynamic analysis.
It's not. There is transfer function, yeah, it's used for dynamic loading, and it's used for dynamic analysis.
But what is the pressure you generate here? Are these steady state simulations or are they?
These specific one are steady state.
So it's static, it's a static load there.
Yes,
You don't have a load over time.
but the thing is, okay, so these are a steady state, but the thing is that with the turbulence length scale on big buildings, so the idea is that the pressure, or the turbulence is, the scale of turbulence is around like 50 meters or 100 meters. So, what it means is the changes occur in the time scales that we can think of it as there is the scale separation between, what happens on small scale turbulence and a big scale turbulence, so we can think of this one steady state simulation as like a series of steady state simulations.
But here you have one, so it's really a pressure map, it's a static, I mean, it's not a pressure over time, it's just a distribution.
Yes, but then what I can do is we can change the angle of attack. So what we would run.
No, but that's more useful, in fact, for the analysis. So it means that you could, for example, if you do some of the analysis, you could define a pressure profile that the engineer would use to do their static analysis.
What they would do is to extract drag and lift coefficients from the simulation and then apply these two buildings.
Yeah.
So,
This is my point. I'm trying to understand how you could recommend it for use from the practitioner. Which could be a good.
That is not difficult. Like the industry knows very well how to use computational fluid dynamics.
I'm not familiar with this. This would be part of the job of a structural engineering office, and they don't use this.
I guess it would be more that the manufacturer uses them to verify their product and then give drag and lift coefficients to the.
But then if you want to design this building with this facade, I'm saying, look, if you're a structural engineer, you need something
not just
that
like
complies with
coming from wind engineering. This is not a problem. Like the use of wind tunnel testing and CFD, or complementing the structural analysis and getting wind loads out of CFD is not a problem. The problem was to simulate these structures in, like, how do we put them in the CFD?
But you're more from, like, it's not a problem to do these things. The problem Eleni is asking is like more that most of the civil engineers never saw a CFD simulation in their life.
Yeah,
but
They will not be able to apply this. I mean,
but they don't have to. The ones that don't deal with high-rise buildings, for example, they don't need to see a CFD, and this is not for them. And people and the civil engineers that deal with wind loads, they will have to know what CFD is
I
like.
think that's quite optimistic.
Come on.
Yes, they can only essentially implement what can be handled by their software, and that's why I was asking you what kind of load that is handled by their software. This could be, and it's convenient that it's a steady state because it means the distribution you cannot.
Yeah, I mean, from my memory, when I was doing wind engineering for low-rise buildings where it's not, the aerodynamics are not that important, and you're right. Steady state, just a pressure load and proper the safety factors and everything, combination factors just gets loaded into software, and it is just a load, yes. But when we are talking about like high-rise buildings, like for example, like this one, it's not going to be handled by civil engineers that don't know anything about wind loading. Like extremely slender high structures, they're designed for with aerodynamics in mind. So it's not just static load, because there are a lot of transient effects that start happening, and
Nice.
Toward the end, you showed the forces and how they change with respect to the angle of attack.
yes.
I suppose one of the plots shows the lift and the other the drag.
Yeah, in certain sense, yes.
Okay, so if you go to the next slide,
Hmm?
if you go to the next slide. A few more, yeah. How can the, yes, here.
Yes.
How can the drag change sign? How is this possible?
Ah, it's because at these like extreme angles, what happens is that the flow separation, energy on like it's a good thing, but it has to do with just the aerodynamics of it.
But like probably this has to do with the domain that you are simulating, if it is. I'm assuming because you assume the boundaries to be so close to your structure, right?
There's there are no boundaries. It's like infinite in all direction.
Ah, in the top right is.
Yeah, I simulate just a part of it, but the numerical condition that I impose is the one, the periodic one.
I don't get how the drag can be in the same direction as the,
As the incoming wind.
Yeah, anyways.
90 degrees angle, it's a limit analysis because you cannot simulate.
Yeah, but it's very close to 90. And it does reverse both lift and drag coefficient do reverse sign. Both from CFD simulations and from physically resolved one and from analytical solution. All I can say is I would have to look nicely into it. I guess, yeah, it's a very good question. I would have to look more close into it. It has to do with, so if you think about like a wing of an airplane, and if you like have some flow over it, it's gonna cause some pressure distribution, and your lift and drag adjust a resultant of one force, which is if you integrate this pressure distribution around your wing, right? And already like on airplane wings, even if like your flow is parallel to the chord, right? You still have lift, for example. So it's not like a very intuitive thing what happens, right? Why does it? So it's probably because when coming at certain angle, the resultant pressure distribution on an array of these things, because it's not just one, you can think of it, it's just like infinite array, is such that it causes let's see. So it causes a sign reversal, so that when we integrate pressure around, the resultant is in a different direction. Okay. But
Are these curves actually perfect signs in cosine?
hmm?
Are the curves actually perfect signs? So you.
No, they're hyperbolic signs and cosines. If you want, you can see
But
the.
the underlying equation is basically has 3 parameters. Like phase and amplitude.
This is the solution, which are, I wrote it as an exponential, but they're hyperbolic sines and cosines. But they're quite, I could not find the reason to rhyme with them even.
But okay, that means you need to fit like 2 parameters.
Yes, yeah,
You need to fit the phase and an amplitude at the end. And then you have here, then you can predict it for every angle.
yeah, I haven't thought about it in that way. I haven't thought about it that way, but that's an interesting point. That we can think, because I was speaking to these equations, right? And I had to think, the resistance coefficients right away.
If you go back to your plots, I mean, it's basically, they are also, you know, the face is like perfectly shifted by 90 degrees, and then it's like, not this one, the other one. These ones.
But
I mean, they are shifted by 90 degrees in phase. So you need to find the two amplitudes and one phase. And you have all your forces.
I'm not sure it will work with hyperbolic sine and cosine, but probably.
And an offset.
Yeah. It would, if, it's an interesting, I will look into it. I haven't thought about it in terms of just phase and amplitude of hyperbolic sine and cosine function. I think because the problem there is, I think it's not just phase and amplitude though,
Yeah, it's an offset as well.
because
Something wrong. No, it's not good.
so the shape of overall, you say it's offset.
Yeah, I mean, so.
Because like, if you look at, for example, like just in the X forces, right? It's also the shape itself is guided by yeah, I'm not sure it would.
No, but if they are like, at the end, I mean, this means you need only really few points to evaluate the whole for every angle, and you can like basically, you have the angle with a very simple function at the end.
Yeah, so the X is 2 coefficients, so probably it would be possible. Because to reduce it to 2 coefficients, same as Y, so yeah. It's just 2 coefficients, so this is saying it can be, there can be this relationship.
But it would give, again, like applications to practical applications, if you can give them a very simple function which you fit it, they only have to plug in the angle.
Hmm. The problem is that, oh no, actually, you know what? No, not really, because it is 2 coefficients for the Y, but if you look in here, the gradient of pressure, the one that controls X, depends on also on your Y flow, right? So
Yeah, but that's what you see, isn't it? You go, and you see that the pieces are perfectly shifted, then 90 degrees.
it just means that the change in pressure or the force in X is no, it's not 2, but it's actually 4 coefficients that are guiding, because
But isn't it coupling that it's like, that the space shift is the same for both, it's like 2 pi different for both.
I'm not sure what you mean.
I mean, you have like, for the X force, you have the maximum where you have a zero where you have zero crossing, what to say. Never mind.
Any other maybe questions, since we have to close slowly? Online, there is no. If not, we can, I guess, stop the recording, and thank you.